Oxford University. Book collecting, student accepting, application rejecting. I'm fine. But how do we answer their toughest questions? Let's take a look. Also, just a quick heads up, I have got a cold on the back burner, so if I sound very nasally or like I have a sore throat, both are true. So our first question is to describe the bonding in aluminium oxide. First we got to look at the valence electrons. Aluminium's in group 3, so it has 3, oxygen's in group 6, so it has 6. Aluminium is a metal, whereas oxygen is a non-metal, so this is giving us a hint that it's going to be ionic bonding, but we're going to check. So we got the electronegativity values here, and we're going to compare them to the table, which shows us which kind of bonding takes place. And as you can see, the difference between the two is greater than 1.8, so it's definitely ionic bonding. So we draw out our dot and cross diagrams, and we write in our numbers, which is the ratio given to us in the question. Then we look at the shape of the molecule. So the aluminiums can't be next to each other, so they have to have oxygens in between them. This will create a large ionic lattice of aluminium oxide. Next question. How do the double bonds in this hydrocarbon affect its solubility? The obvious roadblock for this question is that it says this hydrocarbon, so obviously you'd be given a hydrocarbon in the interview. Problem is, I don't have that hydrocarbon, so we're just going to do it generically. We're going to do hexane because it's an easy one to look at and it's got enough carbons in it that we can look at multiple double bonds. Starting off with only one double bond, we have C6H12, or hexene. So in a double bond, you obviously have the sigma bond, which is the strongest one, and you have the pi bond, which is the overlap of sideways orbitals, which is weaker, and it's also more easily polarized. This means when you have a polar solvent like water, double bonds are more soluble in water, so alkenes are more soluble in water, and that means the more double bonds you have in a structure, the more soluble that structure is. With stereoisomers, the higher priorities being on the same side means that there's more polarity on one side, so it becomes even more soluble. The next question is, can you draw an alkane where every carbon is in a different NMR environment? An environment is the number of peaks indicating the number of unique proton environments. So, what different groups surround the carbon. It's important to note we're dealing with an alkane here, not an alkene or a haloalkane or an alcohol, just an alkane. And again, we're back to hexane, which is going to help us out. So here there are only 3 unique environments, and you can see there why. Which means you'd only end up with 3 points, because 3 of them are symmetrical. Let's start very minimally with ethane, which obviously doesn't because it's symmetrical. So it just has 1 peak because the environment is the same around both of them. Move on to something like propane, and again, you end up with 2 peaks because 2 of them are symmetrical. So the answer to the question is no, unless you use methane, but it says each carbon, not just the single carbon, which implies it wants you to think about chains. Next question's a bit of a curveball. How might playing in a band help you with chemistry? So I'm a brass player, I'm in a brass band, so I can sort of help with this, but not much. There are obvious ones: teamwork, perseverance, attention to detail, and then there are slightly less obvious ones like higher grades on average, fine motor skills, and pattern recognition. And then the real big one is mistake recovery. So learning from your mistakes is a massive thing in bands, and obviously it's a massive thing in chemistry as well. Next up is compare and contrast electronegativity and ionization energy. So we're looking for the similarities and the differences. So we'll start with the similarities and we'll move on from there. So similarities, electronegativity and ionization are both unique for each element. And they both increase across the period, and I haven't got it written it down, but also up the groups. So they have the same trends when looked at on a periodic table. And then that's all I could really think of. So moving on to the differences. Electronegativity, there's only 1 per element, whereas ionization energies you can have first, second, third, fourth, etc., etc. Electronegativity is concerned with the attraction of electrons, whereas ionization energy is concerned with the loss of them. Electronegativity can be relevant to whole molecules, whereas ionization energy is only ever relevant to atoms. Electronegativity also has no units, whereas ionization energy is an energy, so it's obviously measured in joules. Electronegativity has arbitrary values, whereas ionization energy, these values are calculated. Next question is, why is life carbon and not silicon-based? So obviously these two elements are very similar. They are both group 14, and they are only one period away from each other. This question is also a very good question, as silicon is almost 135 times more abundant on Earth than carbon is. However, at about 300 Kelvin or room temperature, carbon bonds are much stronger than silicon bonds, and this is because of their orbitals. Where carbon's electrons are in its second orbital, silicon's valence electrons are in its third. And whilst this doesn't seem like much of a difference, when you bond 4 molecules to carbon, it has a full outer shell, whereas this is not the case with silicon, as the third orbital can have up to 18 electrons. So even if silicon is bonded 4 times, it does not form a stable outer shell. And it's for this reason that carbon enthalpy is about double what silicon enthalpy is. And the final reason is that silicon to silicon bonds are incredibly unstable in water, meaning it wouldn't be suitable for life at all, considering your body is about 75% water. Not to mention all the fish and aquatic life. The next question is, why do electrons not crash into the nucleus? And this is obviously referring to their opposite charges and the forces of electrostatic attraction. And one of my friends at home is going to be kicking his legs in the air when I say the answer lies in quantum physics. Assuming Newtonian mechanics for a minute, even with the force of electrostatic attraction, with the electron orbiting the nucleus, it wouldn't just fall into the nucleus the same way the Earth doesn't just fall into the sun. Which brings us to Lamor's power formula, which says that any accelerating charge, which an orbiting electron would, because acceleration includes the change of direction, emits EM radiation, the power of which can be calculated using this equation here, which would mean that the particle was losing energy over time, which would eventually mean it would crash into the nucleus. But with quantum, they occupy different wavelengths, and every wavelength has to be above the Rydberg energy level at n equals 1, which is 13.6 electron volts, which means electrons don't radiate energy, which means they stay where they are. So the next question is, what is the significance of bonding in benzene? And what this question means to me is, why is the bonding in benzene different to the bonding in the Chatelier model? Because that variation would have to be significant. So we can see that both of them have the same molecular formula, except benzene is delocalized, whereas the Chatelier model has 3 double bonds. These 3 double bonds mean that the Chatelier model has 2 different bond lengths, one for double bonds and one for single bonds, whereas benzene only has 1 bond length because the electrons are shared throughout the shape. It's again because of this delocalization that benzene doesn't react readily with bromine, whereas the Chatelier model would. So the next question is, how do you make aspirin? And the best way to find out how to make something is to draw it out first. So this is your drawing of aspirin, and also this is its UPAC name, 2-acetoxybenzoic acid. I'm going to start with salicylic acid because it's much easier than starting with benzene, which probably isn't what they want to hear, but I'm going to do it anyway. So the question becomes, how do you convert an OH group into an ester group? For an aromatic compound, at least, the answer is you use acid anhydride. So this is ethanoic anhydride, and its reaction does give us aspirin, and it also gives us ethanoic acid. And then we need to look at the conditions of this reaction, which are some sort of acid catalyst and heat. Then you have to purify it, which involves putting it through a Buchner funnel twice and dissolving it in the minimal amount of hot solvent. Next question is relatively simple. What is the difference between diamond and graphite? We've already covered this in my carbon video. They're both allotropes of carbon, that's the similarities between them. Diamond looks like this when you draw it out structurally, whereas carbon looks something like this, where the purple lines are intermolecular bonds. So as you can see, in diamond there are 4 carbon-to-carbon bonds, whereas in graphite there are 3. And that means that diamond doesn't conduct electricity, but graphite, because it has delocalized electrons, does. And it also means that diamond is rigid because carbon-to-carbon bonds are very strong, whereas graphite is rubbery and it can be easily broken and layers can easily slide over each other. And diamond's tight and regulated structure means that light goes through it, so it's transparent, whereas graphite is opaque and it's quite like black and dark. So what is the cause of Le Chatelier's principle? So Le Chatelier's principle, for those of you who don't know or have forgotten, is that any change to a dynamic equilibrium causes the position to shift to counteract the change. To answer this question, we're going to have to use the law of entropy. And this was new to me, so it might be new to you guys. And what that means is order will go to disorder. And a simple analogy that I learned was, imagine you're building a house of cards. Now, this house of cards is very organized, but it puts the cards under a lot of stress. And eventually it's going to fall into a pile. Very disorganized pile at that. And for the same reasons, when you increase concentration or temperature or pressure, you generate order and stress within the system. And disorder always increases, which is the law of entropy, and so you end up with Le Chatelier's principle. Another way to look at it is with the equation for the equilibrium constant. So if you increase the concentration of B by 30 times, you end up drastically changing the equilibrium constant, which means A, C, and D will have to change. A will decrease and C and D will increase in order to keep the constant, well, constant. The next question is a relatively easy one, which puts me a little bit on edge, but it's what does pH stand for? And the answer is potential of hydrogen. But because of the way you work it out, some people would say power of hydrogen, and they're not wrong. You know, there's no objectively right answer in this case. But I just kind of put down generic facts off that. I said it measures acidity, and that was all I really got for this question. And from that one to a very difficult one, purely because you have to guess how big a building is, estimate the mass of oxygen in this building. So I did my house, this is a small plan of my house, and it ends up with a total volume of 487.5 cubic meters, or this in decimeters. I think it's 487,500. Now, I like to assume my house is at room temperature and pressure, so we're going to use the rule that 1 mole of oxygen occupies 24 decimeters cubed, so we end up with 20,312.5 moles of oxygen. You put that into these equations, which you've been doing since GCSE, and you get 650,000 grams, or 650 kilograms, which is a lot, and I did have to check it like 3 times to make sure I wasn't crazy. And then what determines whether an acid is strong or weak? It's how much it dissociates in water. Really, go and watch Acids and Alkalis Part 1 and Part 2 by me. Strong acids dissociate fully in water or solution, and so they have a very high dissociation constant value. This makes sense because when you have a high concentration of hydrogen, you're going to have a high concentration of conjugate base, and you're going to have very little of the whole molecule. So your Ka value is going to be massive. There's also the number of oxygens, which again I went over in Acids and Alkalis Part 2, so you can definitely go watch that. And in the case where acids only have 2 elements in them, electronegativity can count. Hence, in this one, hydrochloric acid is more acidic because chlorine is more electronegative. Bang! That's 14 out of 28 of the Oxford/Cambridge questions done. Please feel free to join me next week for part 2, obviously. Like and subscribe, and I will see you around. Thanks. Bye.